All right, so this presentation will go over moles and molar mass, and these are going to be core concepts for the rest of the course. We need to get this stuff down, and we need to know it well. We're going to start by defining what a mole is. We'll convert between moles and atoms and molecules and compounds. We'll define what a formula mass is. We'll calculate formula masses from the periodic table. Then we'll define molar mass and relate it to formula mass, and finally we'll convert between moles and mass. So when you see the word mole, you may think of this lovely cute little animal on the right, which is a mole. Actually, the mole is the mascot of the American Chemical Society. It's literally this adorable little like stuffed mole that has a lab coat and goggles. You might want to look it up. Anyway, in chemistry, the mole is the SI unit of quantity. In fact, the mole is sometimes called the chemist's dozen. A dozen is also a unit of quantity, and it's one that is much more easily visualized. The mole represents 6.022 times 10 to the 23rd things. That's a lot. The mole unit applies to literally anything, but practically speaking, we're talking about atoms, because we'll never manufacture, for example, enough paper clips to make a mole of paper clips. There's not enough aluminum in Earth's crust to do so. Like literally, it doesn't exist. So you would be short by a factor of 10 on the mass. Anyway, so why is this number so large? Well, that's because atoms are so tiny. To give an amount that is practical for use in a lab, we defined Avogadro's number originally as the number of atoms in 12 grams of carbon-12. The definition of a mole has since evolved to the current one, where we have 1 mole equal to 6.022, etc., times 10 to the 23rd. But the current one still uses that reference point of 12 grams of carbon-12, so it lives on as a standard, but the number of atoms is just close to what that would be in carbon-12. All right, so Avogadro's number is sometimes given as the capital N with a subscript capital A. When you read it in an equation, that's just so that it's not a surprise if you ever see it. And finally, on the bottom right here, we have a picture of 1 mole of various compounds. The mass of each pile is given underneath, as is the identity of the element. You can see that different elements have different masses for the same number of atoms. In fact, drastically different volumes as well. Recall that most of the mass of an atom is determined by how many protons and neutrons it has. So that number will vary by element, and the mass, by corollary, should also vary by element. This is not a lot of stuff if you look at the piles here, but it is a lot of atoms. All right, let's try using the definition of a mole to do some manipulations. First, we'll determine the number of molecules for the given number of moles of each chemical compound. We're going to use dimensional analysis. So let's start with this 2 moles of CO2. And we know that we need to cancel out the moles of CO2. And since Avogadro's number can apply to literally anything, I'm going to put moles down here, and we're going to put 6.022 times 10 to the 23rd in the numerator. And 10 to the 23rd what? Molecules of CO2. Okay, do not have the best handwriting in the world, but hopefully this is functional. So our moles cancel out. Goodbye, moles. That is a rather dramatic canceling. If you do that. Doop. And we end up with 1.0. I take that back, 1.20. Can't read my own handwriting here. 1.204 And I'm going to use calculator notation here. Use a capital E and then 24. So what is calculator notation? Some of you may actually have it as a mode in your calculators to do this, which is why I'm bringing it up. But basically, E means times 10 to the. It's a shorthand for this. All right, so let's try 1.5 moles of magnesium sulfate. And again, we're going to use Avogadro's number. It applies to literally everything. We'll pretend that looks like an M. And we'll have 6, and I'm just going to shorten it here so I don't have to write all this out because we've demonstrated that my handwriting is not great. And it's molecules. Which I can't abbreviate to MOL because MOL is mole. All right, so if we multiply 1.5 times 6.022 times 10 to the 23rd, we get 9.0 times 10 to the 23rd. All right, so finally, what if we start with a really tiny number of moles? Well, not really tiny, but a tinier number of moles, 5 times 10 to the negative third. Turns out with dimensional analysis, we basically just do the same thing we've been doing, but we should expect a smaller number. So we have 6E 23 of CaCO3 makes how many? 3.0 times 10 to the 21st. Molecules of CaCO3. All right. I hope that wasn't too painful. Let's give the next thing a try. We're going to determine the number of carbon atoms we have in 1 mole of the following. So this is an exercise in representing that your chemical formula is a mole-to-mole ratio. That is a thing that we get out of the law of multiple proportions. So it's fixed. It always works that same way every single time, and we can use that information as a conversion factor. What? True story. All right, so we have 1 mole. So we're gonna add that to this label here. And now we're going to make a correlation between the moles of oxalate, that's what that is. It's a polyatomic ion called oxalate. So we're gonna put a mole of oxalate down here. And we want to put moles of carbon in the top. So how many carbon atoms do you have in a oxalate molecule? 2. It has the subscript of 2. All right, so we have now successfully converted between moles of oxalate and moles of carbon. But we haven't gotten to number of atoms. We will get that from Avogadro's number. And again, I'm going to abbreviate this because my handwriting is atrocious. But in this case, it's an atom because we're looking at a specific atom, not the entire molecule. So we're going to come out with 1.2 times 10 to the 24th carbon atoms. in 1 mole of oxalate. All right, so let's do the same process, but with sugar. That's what C6H12O6 is. Specifically, we're talking about glucose. Now, for 1 mole C6H12O6, how many moles of carbon do we have? We use that subscript, and we have 6 of them. Okay, we're going to do the same thing. We're going to use Avogadro's number. And again, this is going to be for atoms. Okay. Ooh, satisfying. Cancel stuff out. So nice. Okay, and so then what are we left with? If we take 6 times our 6 times 10 to the 24th, we will get 3.6 times 10 to the 24th. Sorry, I was reading the wrong line of my notes. So this should be 10 to the 23rd. Boy, I hate it when I do that. All right, so that's the number of atoms of carbon. All right, so hopefully that wasn't too painful. We're really just using dimensional analysis to get from A to B, but we have to remember both the definition of Avogadro's number and the fact that we can flip it whenever we want to. And we also need to remember how the law of multiple proportions works. So let's carry onward. What is formula mass? It is the sum of the average atomic masses of atoms represented in a chemical formula. Now, what does that mean? Well, for molecular compounds, formula mass is for an individual molecule. Sometimes it's referred to as molecular mass. But for ionic compounds, it's the mass of the smallest unit of a larger crystal. Additionally, because we have cations and anions, the cation is slightly lighter because you've lost an electron or more, and an anion is slightly heavier because you've gained an electron. But an electron is 1,000 times lighter than a neutron or a proton, and overall you have no net difference in the number of electrons. Therefore, we're just using the thing off the periodic table the same way that we do with molecular compounds, but know that's for a smaller unit of a larger thing. All right, let's go ahead and calculate the formula mass for the following. So we're going to start with KNO3, potassium nitrate. That's that polyatomic ion. And in the bottom right here, I have pulled the atomic weight, the average atomic weight from the periodic table. So let's do this thing. Potassium is 39.098. And this is AMU, or atomic mass units. Then we're going to add nitrogen at 14.07 AMU. And then finally, we have oxygen. But there's 3 oxygens because we've got the subscript. So we're going to multiply our mass of oxygen times 3. And I've given it as 15.9995 because that's what was on my periodic table, but I am going to be lazy and round to 16. Because we only have to the hundredths place for nitrogen, so it's really not going to make a difference if I round that. All right, so if I add all of those together, 39.098 plus 14.07 plus 3 times 16, I get 101, and we're going to round it to the hundredths place, and I will get 17, and it's AMU, or atomic mass units. All right, so let's do the same thing, but we're going to do it for H2CO3. Now, in this case, we have an acid right? It's because we've got hydrogen with a polyatomic ion, and we know that that's an acid. CO3 is carbonate, so it's carbonic acid. All right, so let's try to do the thing. We have 2 hydrogen atoms. So we're going to do 2 times that weight plus, oop, forgot the unit. That's a problem. We always want to include the units because when we mess up, we all have our stupid moments. It is much more obvious that we messed up if you include the units. If you don't include the units, you can end up with things like liters squared per meter unit, and it doesn't make any sense. And you're like, well, that was dumb. Whatever I did, it didn't make any sense. Okay, so we've got carbon, and then we have 3 oxygens. We're going to do 3 times 16 again. And we'll pretend that all of these look like AMU, even though they really, really don't. Sorry. So 2 times 1.008 plus 12.011 plus 3 times 16 gives you 62.03. And again, this is in atomic mass units. All right, so this is not super difficult to do. Basically, as long as you have a periodic table, you can find a formula mass, which is snazzy. But there's another concept we call molar mass. So what is the difference? Molar mass is the mass in grams of 1 mole of a substance, and we give it with the unit of grams per mole. Molar mass is generally what we use when we're doing our calculations. It is numerically equal to the formula mass that we just calculated. But the unit is different. So instead of AMU, it's grams per mole. So what is the relationship between AMU and grams? AMU is the mass of 1 atom, and molar mass is the mass of Avogadro's number of a substance. So 1 AMU is equal to 1.66 times 10 to the negative 24th grams, which is super tiny. All right, so in order to convert from mass to moles, we need to use the molar mass. And in order to do that, we have to add up the mass of each of the elements in the substance. So let's do this for potassium permanganate. MnO4 is the permanganate polyatomic ion. All right, so we've got potassium 39.098, and I'm going to omit the AMU because this is me trying to find grams per mole. Manganese 54.94, and then we have 4 oxygens, so 4 times 16, and when we add all of that together, we get 158.03 grams per mole. Okay, now we can take that and use it like a conversion factor. We have 158.03 grams in 1 mole of the substance. Those values are equal. Okay, so if we're using it as a conversion factor, we have grams on the top here, so we want grams in the bottom here. So we put 158.03 grams on the bottom, and then that flips the mole to the top. So the grams cancel, we end up with moles. All right, so if we do that calculation, fairly straightforward, 3.5 divided by 158.03. We get 2.2 times 10 to the negative second moles, KMN All right, we're going to go ahead and do this process a second time so that hopefully it makes even more sense. So again, first thing we have to do is figure out the molar mass of the thing. So for calcium phosphate, which is what this is, 40.08 times 3, because we've got 3 calciums. Now this gets a little bit tricky because our phosphorus here is in parentheses, as is our oxygen. So we want to distribute that 2 subscript into the parentheses to get the proper number of atoms. So that'll be 30.97 for our phosphorus, and there's 2 of them. And then we'll have 16 for our oxygen, and there's 8 of them. So if we add them all together, what? 310.66 grams per mole. All right, now when we apply that, again, we want the grams in the bottom. And that mole flips up to the top. So I'm just going to erase it from down there. Boom. Okay, so now the thing that we don't want cancels, and the thing that we do want is remaining, and that gives us 2 in rounds times 10 to the negative second moles of calcium phosphate. I'm not going to write it out because that will take forever. All right, now what about wanting to go from mole to mass? Again, we're going to need the molecular weight. So what is the molecular weight of, what is HCO3? You look it up. Bicarbonate. Sodium bicarbonate, aka baking soda. All right, so we take our 22.99 and we add 1.008 and 12.011, and then 3 times 16. Okay, so again, we're just taking each one of the molar masses, or the atomic weights rather, and we're adding them together. This is not a difficult process. We just have to make sure that we're accounting for everything. So we get 84.01 grams per mole. All right. Now, in this case, we have moles to start with, so we can leave moles in the denominator. So we have our 84.01 grams per mole. Moles will cancel. And we take our 4.75 times 10 to the negative fifth and multiply that by 84.01. Okay, now I will caution you. You either need to make sure that stuff is in parentheses, or you need to make sure that you're rounding. Sorry, we need to round this number. 4.0 times 10 to the negative third grams of baking soda. Okay. And we'll try another example, but with nicotine. I've given you the molecular weight of nicotine, so we don't have to go through that process of finding molecular weight again. But 8.4 times 10 to the negative seventh, make that a better 8. Still bad. And then we just multiply by molecular weight. which in this case is 162.2 grams over moles. What does that equal? All right, I get 1.4 times 10 to the negative 4th grams of nicotine. All right, that wasn't so bad, right? We're just using dimensional analysis, and we need to recognize that our molar mass can go either grams per mole or moles per gram, and both of them are equally valid. To summarize, a mole is Avogadro's number, N sub A, of things. It is 6.022 times 10 to the 23rd. Formula mass is the sum of the average atomic weights associated with a chemical formula. Molar mass is the mass of 1 mole of a substance. Numerically, the molar mass is equal to the formula mass, but the atomic mass units are for a single atom. So 1 AMU equals 1.66 times 10 to the negative 24th grams. In other words, AMU is tiny. Molar mass is a pretty normal number. Convert between mass and moles using the molecular weight and using dimensional analysis. The molecular weight can act like a conversion formula or a conversion unit.